Hello everyone, my name is Jair. I'm from the Laboratory of Mathematical Modeling and Algorithms at University of Tsukuba, Japan. We worked on this research when I was first year masters, and I hope it will further expand the discussion in our field. I'm looking forward to discuss with you in the Q&A section. Let's start the presentation. In this presentation, I'll talk about the use of evolutionary algorithms to design other evolutionary algorithms, and also some training strategies for hyper-heuristic. Let's get started. There's a need to have algorithms tuned to a specific type of problems, problem instances that have some common underlying characteristics. When preparing those algorithms, we need to tune not only its parameters, but the whole design itself. Instead of manually designing the algorithm, we can use evolutionary algorithms to automate this task, and there are great interest in doing so. However, the design of a good fitness function for this task is very hard. If we are not careful enough, we may use a fitness function that is too easy, and the system then simply does random search. We also may use a fitness function that is too hard, and the system, this time, may not find valid solutions. We noted these challenges in our previous work, and now we try to work on them. In this new research, we test two ideas. First, what if we start the training on easy problems, and then, as time passes, we increase the difficulty of those problems? Will we observe an improvement on the generated algorithms? Second, we know meta-heuristic parameters are very important, but search for design and parameters hugely increase the search space. If we ignore these parameters during evolution, how detrimental will it be? Before we dive into details, let's first take a look at our system for program generation. Then, I'll go back to these approaches to avoid those problems. A well-known way to generate programs is genetic programming. It evolves candidate algorithms, just like genetic algorithm evolves candidate solutions. In our work, we use grammatical evolution, which is one special type of GP. It uses grammar to restrict the search space. The grammar is composed of production rules and terminals. Now, moving to our framework, the production rules were derived from a pattern that we identified in most meta-heuristic search algorithms. And it is this pattern here. First, a set of candidate solutions are initialized, that's the population. Then, while the stop criteria is not met, some candidate solutions are selected, and those selected ones are then modified. Lastly, replacement decides which candidate solution will stay in the population for the next iteration. After looking at this pattern, we wrote a grammar that expresses it. Now, the terminals, also called primitives in the hyper-heuristic context. Here, we are seeing only a brief overview, so for more details about the meta operators, please check our paper. Okay, starting from the production rules. Let's expand selection. We have many ways to do selection, for example, tournament from genetic algorithm. Likewise, for variation, there are crossovers, mutations, also from GA, and some other operators like Levi-Flight from Google Search. And finally, some examples of replacement, the rule that decides which candidate solution will be part of the new population. So, to summarize, the grammatical evolution generates candidate algorithms based on the grammar and primitives. Those candidate algorithms are evaluated on the target problem. Then, GE evolves those candidate algorithms. We expect that GE captures underlying characteristic of the problem, so we can use the generated algorithms on other problems with similar characteristics. As a result, we get a program that looks like this one here. As we talked before, we need to be very careful when designing the training of the hyper-heuristic. If the fitness function is too easy, then any candidate algorithm will do. But if it's too hard, then none of the candidate algorithm will solve the problem. In both cases, it's likely that evolution won't happen. Another related problem is, if we include parameter tuning as part of the grammar, it will hugely increase the search space with many similar algorithms. On the other hand, if we completely remove the parameters from the search, it will negatively impact the evaluation. Tackling the first problem, we propose a training schedule in which the training starts easy and gets harder over time. So, for example, in a traditional training, all the evaluations would be done on the sum function, same difficulty. And the difficulty here of the problem is represented by the dimension. But in the first few generations, we could use a easier version of the target problem. It could start at 2 dimensions and move that to 10, or start at 5, or even a more granular increase. Now, for the second problem, we compare the generated algorithms of a grammar that includes parameters against the ones from a grammar that does not include it. For the first grammar, the parameters are discrete instead of all infinite numbers in an interval. For the second one, every time a candidate algorithm runs, it uses a new random set of parameters. One detail from the experimental design that is very important. Every candidate algorithm was evaluated 5 times. We used only the best fitness from these repetitions. For the grammar without parameter, it means it ran using 5 sets of different parameters, while for the grammar with parameters, it ran using exactly the same fixed set. Okay, we had those 2 problems. We then made 2 suggestions. Now we have to test them. We want to answer whether training first in lower dimension will produce a better algorithm than training straight in the targeted dimension, and how much impact will it have when ignoring the meta parameters during the search. The results. To start, we trained our framework on a series of problems using different training schedules and for both grammars. An algorithm was generated for each situation, and then we tested it on similar problem. And the similar problem is a different instance of the sum function used in the training. The results here are all from the testing. This figure is the empirical cumulative distribution. Each of those figures that I'll show is the performance on a specific function, and each function has 15 instances, the random variations of the function, and each instance has 51 targets. The x-axis is the number of functions evaluated in logarithmic scale. The y-axis is the pair of instance target. It shows the percentage of problems solved from 0, nothing, to 1, everything. Each line in the figure represents a generated algorithm from different training schedules. For easy identification, I named the algorithm after the training schedule. For example, the 210D is the one that was trained first on 2 dimensions and the next on 10 dimensions. For this figure, in short, bigger the area under the curve, better. For this presentation, I'm showing the results on only 2 functions, attractive sector and Gallagher's 101. Those are the functions 6 and 21 from the COCO benchmark. Okay, grammar with parameters. Training straight in 10D generated the worst algorithms compared to the other scheduled. For attractive sector, we had two generated algorithms that solved all problem instances. For Gallagher's 101, the only algorithm that had a clear difference on performance, and for the worst, is the one trained directly on 10D. Between the training schedules, the ones highlighted here had the best performance. This figure suggests that 2D was a good start point for the training, and it also may suggest that a more granular change in difficulty may improve the training. A point worth noting here is that the algorithms at the left are all different from the ones at the right side. Now, the same type of figure, but comparing the grammar that does not include parameters. Here, there's just no clear difference. It seems the training scheduling does not matter. Maybe the parameters are less sensitive to different dimensions compared to the primitives. Last figure, I pick one algorithm from the grammar with parameters, and I pick another from the grammar without parameters. And I compare them to DE, differential evolution, and PSO, particle square optimization. Those last two, they had their parameters stamped using arrays. In this context, the algorithm without parameter is not the best, but it also seems not that worse. As for the one generated from the grammar that includes parameters, it had a good performance compared to the other, solving all problems instances on function 6 and almost all on function 21. As a conclusion, for the training schedule, starting the training on an easier function was effective, and more granular change in difficulty may improve even more the training, something that we can explore in a further research. Grammar without parameters. It was overall worst, but not that worst. The parameter seems less sensitive to the change in dimension, as the operator seems more sensitive to the change in dimensions. So how better distribute those training resources? Well, that's it. Please, if you want to take a look at our research or get in touch, there is the QR code here to my page. And really thank you for your attention.